We design a lot of systems, from organizations to pieces of technology, with the idea that they'll improve over time. But what we often see is something strange. The very efforts we make to fix them can end up making them more rigid, more fragile. So in this explainer, we're going to examine the underlying mechanism that drives this process and see how a series of perfectly logical decisions can lead to a deeply illogical outcome.
The whole puzzle here really starts with a broken expectation. We have this very common assumption that when you fix a problem, the system as a whole gets stronger, more effective. But the observation, what actually happens, is that the very act of layering on these fixes often leads to more complexity, and you end up with a system that actually resists any kind of real fundamental change.
To understand how this happens, we really have to go back to the beginning and look at a system in its initial state.
So a new system often starts out in a state of, let's call it high coherence. Its different parts are what we call loosely coupled. That just means a change in one area doesn't really cause huge ripples in another. And this structure, well, it gives the system a ton of adaptability. It can respond to new demands pretty easily. But of course, no system exists in a vacuum. Sooner or later, it's going to run into some kind of pressure that forces it to make a choice. This pressure comes from the outside world. Maybe it's a new requirement, a new competitor, or just a change in the environment. And it introduces a stress that the system, as it is, just can't handle. It has to be modified.
And this need to change presents a really critical fork in the road. The system is forced to choose between two very different paths forward.
Okay, so the first path is what we'll call the refactor. This means you go back and do a fundamental redesign of the system so that the new pressure fits right into its core logic. It's the right long-term solution, but it has a really high short-term cost. The second path is the patch. This is just a localized workaround. It solves the immediate problem quickly, it's cheap, but it doesn't actually fix the underlying structural issue.
Now, this choice between the two paths brings up a really important concept called path dependence. All this means is that decisions you make today constrain the choices you'll have available tomorrow. So the path you pick right now is going to have a huge impact on how the system can evolve in the future.
And choosing the patch, well, you can think of it like taking on debt. In this case, it's called technical debt. You're picking a quick, easy solution to hit a short-term goal, but that decision comes with a hidden future cost. That debt is going to have to be repaid down the line, and usually with interest.
But here's the thing, and this is absolutely crucial to understand. The decision to apply a patch isn't a mistake. Not at all. When you're facing immediate constraints, like tight budgets, impossible deadlines, or just not enough people, the patch is actually the most efficient, the most rational use of your resources. It's the optimal decision at the local level. So that initial choice, that very sensible, locally optimal decision, it kicks off a self-reinforcing cycle that starts to drive the whole system's evolution.
What you get is a positive feedback loop. When the next pressure comes along, the system is already a little bit more complex because of that first patch. This means the cost to do a big refactoring has gone up, while the cost of adding just one more patch is still pretty low. So the patch gets chosen again. And this, of course, makes the system even more complex, which in turn makes any future refactoring even more expensive. You can see the cycle.
You see, each patch doesn't just add a single component. It adds new connections, new dependencies. Parts of the system that used to be separate are now tangled together through this web of workarounds. And all this technical interrelatedness makes it much harder to predict or even understand how the system is going to behave.
This whole cycle is a perfect example of what's called increasing returns. All it means is that the more the system goes down the path of patching, the more efficient it becomes, in the short term, to just keep going down that same path. The cost of doing anything else, of choosing to refactor, it just grows and grows with every single patch.
Over time, the accumulation of all of these layered fixes starts to lead to a really critical long-term consequence.
After many, many cycles of this feedback loop, the system isn't that clean, adaptable thing it was at the start. Now it's a tangled web of interdependent fixes, where every little piece is sort of precariously balanced against all the others. The whole thing becomes brittle, opaque, and really fragile.
Ward Cunningham, who was the originator of this technical debt metaphor, he summed up the ongoing cost perfectly with this quote: "Those interest payments he's talking about, that's all the extra effort and resources you have to spend just to work around the system's own complexity for any new task."
And eventually, the system can hit a point where those interest payments just consume everything,
All the available energy is being spent just to maintain the existing patches, to navigate the complexity, and to fix all the little failures that are bound to pop up from this brittle structure. There's no capacity left for anything else, certainly not for innovation or any real improvement. Now, the system hasn't failed in some big, catastrophic event. Instead, it's just reached a state of gridlock. This extreme rigidity, it's an emergent form of failure. It's a property that arises from the entire history of interactions inside the system, not from any single bad part.
So, this entire mechanism reveals a much broader principle about how complex adaptive systems tend to evolve over time.
What we see is that a system's evolution is governed by this kind of internal logic. Its history, and especially those small choices made early on, constrains what's possible in the future. Those feedback loops we saw amplify the effects of these initial decisions, and all the while the system is co-evolving with the pressures from its environment, which tends to lock it into one specific path.
And this brings us to the central paradox of the whole process. Each individual decision to apply a patch was the right one, the optimal one, based on the circumstances at that moment. But the accumulation of all these locally rational adaptations produces a globally dysfunctional state, a system that's gridlocked, fragile, and pretty much incapable of meaningful change. This outcome really reveals a fundamental tension in any evolving system. The constant pressure for local, short-term optimization can inadvertently create long-term systemic fragility. Understanding this dynamic is really key to seeing how systems can fail, not with a bang, but through a slow, quiet descent into rigidity.